All right, so here we go. I'm going to record and I'm going to mute you all. Yes. All right, so I'm going to share my screen and hopefully give me a thumbs up if you see my PowerPoint. All right, so appreciate the opportunity to meet with you all tonight. I know this is a little different. It's always more fun to meet in person, but well, here we go. So I'm going to talk tonight about water and wood with the goal of predicting the behavior of wood. In other words, what is wood going to do as the moisture content changes? And you can see in the picture here, someone put together a nice tabletop and had some problems, right? And they posted online somewhere, you know, what is this? Why did it happen? We're going to talk all about that tonight. Now, I know a lot of you are very experienced woodworkers and may know quite a bit about the subject matter already, but I'm walking into this with the assumption you know nothing, right? So we're going to start at the very bottom and then we're going to kind of roll through some things. And we may not get into the depth that some of you want, but I think for entry level, this is going to be a good introduction. And I'll start off with, you know, just an outline of what we're going to do. That's me a very long time ago before I was gray hair. But you'll notice that piece of wood, you know, some of you are probably like, oh, I wish I could get my wood to bend like that for this certain project. Well, the commercial drying operation that had that piece of wood wanted it to be straight, right? So why did it do that? That is, I think, what is that? That is cottonwood. That is cottonwood from Mississippi. That's down at Anderson Tully down in Mississippi. Cottonwood has a lot of reaction wood in it that I'll define later, which causes it to do that. So our outline, you know, why does wood do that? You know, why would it do something like that? Well, we're gonna figure that out. But first, we got to talk about some basic things like, why does wood like water? What is it about wood that makes it hygroscopic? It absorbs water, it gives up water as the amount of water in the environment changes. So we're going to introduce that. But in order to do that, we've got to talk about moisture content. You know, just what is moisture content? What should it be? You know, if I'm going to be doing woodwork, what should the moisture content of my wood be? And then why does it change? What is it about wood and moisture that allows it to change? I mean, is there anything I could do to prevent that? And then we're going to talk about what happens when the moisture does change. You know, wood moves. We know that. Well, exactly how does it move and why does it move the way it does? And in order to do that, I'm going to go through a little anatomy lesson, and we're going to talk about planes of reference, which hopefully you're already familiar with, but we'll go into that in great detail. Then finally, we're going to do some calculations. Hopefully you have the handouts that I sent, but they'll be up on the screen if you need those. We'll talk about what normal wood would do given a change in moisture content and show you how to calculate that. So you might say, what is my tabletop going to do if it changes 2% in moisture content? Well, after tonight, you'll be able to calculate it. And then finally, some of you are just going to be like, forget this. This is too difficult. Is there anything I can do to just avoid this problem? And we'll talk about some of the things you do to reduce the influence of moisture in wood. Before we get started, I can't spell reference up there evidently, but these are the reference materials. I put them in the handouts. The wood handbook is definitely a reference you want to have. Everything we cover tonight will be in that reference material. To get that, you just type in the wood handbook. It's downloadable from the Forest Products Lab in Madison, Wisconsin for free. It's a PDF. You should have a copy of that. Another great reference, which you probably already have in your library, is Understanding Wood by Bruce Hoadley. Bruce Hoadley was a wood scientist at the University of Massachusetts. He took a lot of scientific information about wood and put it in a very readable and understandable format. So both of those are great references. And you know, if you have other questions tonight about the material, take a look through there and you'll get the same level or even greater level of detail. So wood and water, what about it? So wood is a hygroscopic material. It is always changing to try and reach an equilibrium with the amount of moisture in the wood to the amount of moisture that's in their surrounding environment, right? So if the surrounding environment has very little moisture in it, the wood's going to dry out. If the surrounding environment has a lot of moisture in it, like it does right now, it's raining outside, it's going to pick up moisture. And Wood expands when it absorbs water. We're going to explain why. And wood shrinks when it loses water, and we'll explain why. The amount of water in wood is always changing. So some of you may have heard, or if I kiln dry this to 8%, it's never going to change, right? That is not true. It will always try to reach an equilibrium with the surrounding environment. And a lot of times this is bad for us. We don't want wood to move. We don't want it to change. We want it to be very dimensionally stable. If you look at the ruler here, this is a 12-inch ruler, and there's about an 1/8-inch gap on each side of that ruler in this floor. This is a 6-inch wide plain sawn beach flooring. It was installed too dry in this home, and now we've got some movement in there based on absorption of water. So it causes problems for us. So let's start off at the beginning, right? Why does wood like water? How many of you are interested in a chemistry lesson tonight? Don't say anything. Okay. So let's go back, let's look at wood in general. Wood is a natural composite. A lot of times we think of wood being very simple, right? It's just a board comes from a tree. But, if you think about it, wood, lumber, is basically a group of, it's a composite of cells. And those cells have an orientation. So if you look on the left side of the screen here, you'll see that's wood magnified significantly. And those are all cells. And the majority of those cells are oriented to move water from the roots to the leaves, and then nutrients that are in water back from the leaves to where growth occurs. So the majority of those cells are oriented in plane from the ground to the top of the tree. There are some cells like these wood rays that move transversely through the piece, but it is a composite. It's a composite of cells. So we're going to start there, and then we're going to move to the individual cells. So these are the individual cells. There are different kinds. And then if you look in the middle there, each cell is made up of a composite of four parts. There's a primary cell wall, the secondary cell wall, and the tertiary cell wall. And all of that is further made up of something called microfibrils. If you look carefully at that little diagram, you'll see the orientation of these lines. That's actually called microfibrils, and that controls how wood shrinks and swells. But that is actually made up of chemicals, right? And wood is made up of cellulose, hemicellulose, and lignin. And you're like, oh my gosh, I don't want to get that deep. But cellulose itself is made up of sugar units called glucose. And you'll see the wonderful chemistry diagram here of a glucose unit. Glucose is a simple sugar. But what you'll see repeated in there is hydroxyl groups. If you think back to high school chemistry, hydroxyl, what does that mean? The H is hydrogen and the O is oxygen. And you'll notice each of those groups is bound by these hydroxyl groups. And so you get a long polymer chain of cellulose tied together by these hydroxyl groups. Well, what else happens to have hydroxyl groups? Water does, right? Water is H2O. What is H2O? It's 2 hydrogen molecules and 1 oxygen. Okay, so let's go back to wood. If I've got 2 microfibrils or 2 cellulose chains that have hydroxyl groups, these areas up here, these OHs, maybe I can draw on here. Let's see if I can draw on here. Annotate, draw. So if I take one of these units here, these OH units that's all by itself, that hydroxyl group is attracted to another hydroxyl group, which is what we're looking at here. If there's no water present, they will move closer together. Okay, so let's say there's a real humid environment. Those hydroxyl groups don't actually chemically bond. They're still attracted to other hydroxyl groups. So you can take a bit of water. Let's see if I can draw it in here again. I can take some water and put it in right here. And the hydroxyl groups in water will bond to the hydroxyl groups in the wood, but you've got to push it aside to make some room for it. Hey, guess what? If you put water in wood, what happens? It expands. Believe it or not, it's all the way down on the molecular level, which is causing this to happen. Now, if I take my water molecule and I take it out of there, move it in this direction, then those hydroxyl groups, they've got a big space in there, and they'll actually, since they're attracted to one another, will move closer together. So believe it or not, wood shrinks and swells because of the hydroxyl groups in cellulose and hemicellulose at the molecular level. These molecular changes cause wood to change in dimension at the macro level. Woo, that's probably all you ever want to know about the chemistry in wood. But that explains why wood is attracted to water. It's these hydroxyl groups, this hydroxyl hydrogen bonding and hydroxyl groups that there's a reason why water is attracted to wood, or wood is attracted to water. All right, now how do I get back to this? Let's see, here we go. So that's why wood likes water. Now let's talk about how we measure the amount of water in wood. You have to be careful here, because most woodworkers and most people using wood for a finished product talk about measuring moisture content on the oven dry basis. We don't say oven dry basis, we just say, hey, what's the moisture content of the piece of wood? However, 90% of the time what we mean is the oven dry basis. The reason for that is the material or mechanical properties of wood, we can kind of predict what's happening if we know what the moisture content is based on the oven dry basis. Now, other folks like the pulp and paper companies, they'll measure it on the green basis. And in the green basis, that would tell us what percentage of the wood is actually full of water. On the oven dry basis, it's not, okay? It is the weight of water in wood relative to the dry weight of wood expressed as a percentage, a very different thing. So if we look at my diagram over here, this purple piece of wood that's a cross section of wood. It's the wood and the water in wood. So if I take the water out of wood, I've got water, and then I've got the wood. And if I take the mass of that water, and I put the mass of that water over the mass of the dry wood, that is the moisture content, okay, based on the oven dry basis. So if I get a moisture content of 50%, that does not mean that 50% of the wood is water. That means the ratio of the weight of water to the dry mass of wood, or the dry weight of wood, is going to be 50%. And yes, I interchange mass and weight, because a physicist will get on me about that, but in general terms, we can do that. So moisture content, we calculate moisture content this way. We take it's often labeled as the green weight. You can just say initial weight, the first weight that I take. Then if I oven dry that piece out, I subtract that. And if you subtract the oven dry weight from your original weight, that tells me what? That tells me the weight of water that was in that piece of wood. If I divide that by the oven dry weight, then I get the moisture content. I'm going to multiply that by 100, because this is a percentage. Okay, that is how I calculate moisture content using the oven dry weight. There's actually an ASTM standard for this. So it's a very standardized, normal way of determining moisture content, okay? So it's the ratio of the weight of water to the weight of oven dried wood. It is a ratio. Can I have over 100% moisture content? Yes, I can. So think about balsa wood. If you have a volume of balsa wood, what is in most of that volume? Air. So imagine if you put water in all that void space, what would weigh more? The dry mass of wood, or the amount of water that was contained in the wood? The amount of water contained in that volume would be significantly greater in weight than would the oven dry mass. So species like southern yellow pine, when you first cut a southern pine tree down, the sapwood commonly has a moisture content over 100%. Most species do not. Most species, your oaks and your yellow poplar and most of your hardwoods, typically have moisture content somewhere between 65 and 85% when you cut the tree down when it's alive and growing. So how do I get this? Like if I wanted to measure this myself, what would I do? Well, in the lab, what we do is we take a 1-inch section out of a cross section out of a piece. We put it on a scale. We throw it into an oven. Yep, that's why it's called oven dried. We dry it out completely. And then when it's completely dried, we put it on a scale. Your first question is probably, how hot is that oven got to be? We put that oven at just above 212 degrees Fahrenheit, about 220 degrees, just above the boiling point to accelerate the drying. You do not want to dry it too high a temperature, because you can break down other components in the wood that would lead to a mass loss, but not actually a moisture loss. We'll leave that piece of wood in the oven until it loses all its moisture. So your next question is, well, how do I know when that is? I can take that piece of wood out of the oven, put it on the scale, weigh it, write that weight down, put it back in the oven for about 2 hours, pull it out, weigh it again. If the weight is the same, that means it's completely oven dry. If the weight is lower, that means it's still drying out. And that's a simple thing you can do. You can do that in your oven at home. It's fairly simple to do. And then you just take the numbers. So if we look at my initial weight, it's 90 grams. So 90 grams is going to be my green weight in my equation. My oven dry weight is going to be 60 grams. So that's going to go on top here. That's going to give me a water weight of 30 grams. My oven dry weight is 60 grams. Multiply that by 100. I get a 50% moisture content for that particular piece of wood. Okay. Now, most of you probably don't use that technique. You probably use something like a moisture meter, a simple technique. It basically relates the amount of moisture in wood to an electrical property in the wood, right? And so these are fairly accurate, between 6 and say 28 or 30% moisture content. They have limitations, but it's another way for you to measure moisture content. Now, we could spend a whole evening talking about how these work and the advantages and disadvantages, but basically they work very well between about 6 and 28% moisture content. They'll give you the same information as the oven dry. However, there's a couple things we need to think about in regards to this term called moisture content. If you think about it being done on the oven dry basis, it's taking an average of all the moisture in that piece, right? You're drawing all the moisture out, so the equation doesn't tell us where it is. So let's assume my drawing here is a cross section of a piece of wood. And if I say, hey, I want my wood at 8%, because most of you are thinking, hey, you know, I read somewhere in a magazine, if I'm building interior woodwork, it should be between 6 and 8%. Well, ideally, what we think of is that the outside of that piece is at 8%, the middle, the halfway into that piece is about 8%, and the dead center is probably at 8%, right? That would be an average of 8%. That's basically what we want. We want uniformity so we don't have any moisture changes or dimensional changes while we're working with wood. But hey, guess what? This cross section is also an average of 8%. How could this possibly happen? Well, I picked up a piece of wood from my local wood dryer. I took it home and I started making something out of it. I ripped the piece in half and I chopped it to a shorter length, and then I had to go away for a week. And I came back on Saturday and it had moved. Well, what had happened? Well, that piece was actually at 8%, which is exactly what he said it was. But actually the outside is down around 5. A little third of the way in is around 7, but in the center, it wasn't completely dry. So if we'd have done an oven dry test, it would have said, hey, this is at 8%, it's ready to go. But be aware that sometimes it's not the average that we're interested in, it's the gradient from the outside to the inside. I don't want that piece to be more than 1% or 2% difference from the outside to the inside, or that wood is going to warp on me while it's in my shop and once I've started cutting it into pieces. And this is a very common problem with dried wood. Now I'll tell you a little story. So I'm a woodworker too. Most of the time I just work rather than work with wood. But I get a project, I get some wood, I get all excited about a project and I get some wood for it. And I'm going to get to it that weekend. Well, then it ends up in a shed outside for about 6 months, right? And then the coronavirus comes and boom, I get time to work on that project. Well, what do you think happened to that wood when it was in the shed outside for 6 months? It's still dry. It still says it's at maybe 8%, but now the inside is actually closer to where I wanted it to be. And now as you move to the outside can actually have picked up moisture. Why? Because the shed outside has a higher relative humidity than inside the house. And so that wood is actually going to pick up moisture. And this is actually a common problem even in the industry. If you store wood in just under a roof or in a shed with the doors open, in the summertime, I've seen red oak pick up as much as 11%, a quarter inch in a piece of lumber. So it does happen. And so this is another example of a gradient where it can cause problems for you. So if I produced a piece out of this, cut this up ripped it into pieces and then glued it into a panel, anything that contained lumber from this piece is gonna shrink and move on me as it's glued into the panel. Okay. So some ways to determine if there is a gradient. If you have a pin meter, you can get insulated pins. They're usually ceramic coated pins. And as you drive the pins in, you can take different readings or measurements as you drive it through the piece of wood. The pinless meter does not work for measuring gradients. It's going to give you something close to the average, just like an oven dried average would be. So that's not going to help you. If you want to do an oven dried slice test to tell you what the difference between the outside of a piece of wood and the inside is, what we call a shell and core test is something we typically do. So we take this to a bandsaw, I cut out this little L on for what I'll call the shell or the outer part of the piece of wood, and I measure this and this separately from the center. And then when I dry them, I measure them separately again, so I can calculate the moisture content of what the outside of the wood was, as well as this piece that was on the inside, right? And that'll tell me what the difference between the outside and the inside is using the oven dried method. These are just ways for you to find out what the moisture content of your wood is and what the distribution is before you get started, because knowing that distribution sometimes is more important than the average, particularly if you're not certain about the person drying your, or the operation drying your lumber, or if you've held that lumber in storage for a period of time. Okay, with that, I'm gonna ask and see if there are any questions about anything we've covered up to this point. Now, if you ask me a question about what we're gonna cover, I'm gonna say hang in there, but if you have any questions about moisture content gradients, or why wood likes water, I'll entertain those at this time.
Brian, a question about equilibrating your wood to shop conditions. I've heard frequently heard the comment, let your wood sit in the shop for a week, stickered, it reaches equilibrium. Is that enough time?
That is a great question, right? You'll hear that with wood flooring too, right? I gotta have my wood flooring reach some kind of equilibrium. I'll put it this way: when we do tests on wood flooring, it takes about 42 days in an environmental chamber at the exact same conditions for that piece to get close to uniform. 42 days to get it even close with a large gradient. So what do you gain by sticking it in your shop on stickers for a short period of time? Well, you're getting it closer, right? You're getting it closer to the target. It may not actually get to that target, but you're getting it closer. And so you're helping to minimize any drastic changes. And you'll hear me say this later, and I'll say it again and again and again and again. The goal is, when you get your wood dried, is to have it dried to the moisture content of your shop, how it's going to be shipped, the moisture content of where it's going, and the moisture content of the client's location and the service life of the piece. If you can do that, the big if there, right? If you can do that, wood will never move.
Can you? Oh,
go ahead, Ross.
Yeah. Can you explain the difference between moisture content and relative humidity?
Yeah, we're going to go there next.
Oh, okay. All right.
Yeah, go ahead. You raised your hand, Bill.
Yeah, Bill. A lot of stuff that I have done has been my tabletops with reclaimed wood, old oak or old chestnut. And I can never tell what's going to be a disaster or not. Is there something unique about a 100-year-old piece of wood that's been, let's say, a roof truss or something in an old factory?
Sure. Everyone thinks that since it's old wood, that it's completely dried, that it's dried where you want it to be. That's not necessarily the case, particularly if it's in a factory. If it's in a factory as a beam, it's probably going to be closer to not outside conditions, but not 6 to 8%. It's probably going to be closer to 10 or 11, could be 12. And so you still want to dry that stuff out to the 6 to 8% when you bring it into your shop. And so a lot of reclaimed furniture places, before they make flooring, they actually put it into a dry kiln to drop it from about 12 to 6 to 8%. So just because it's been around a long time does not mean it's a
Okay. Thank you.
The key is for interior conditions. Okay, and that's where we're going with the next little bit here. Is there one more question, or should we head on? All right, let's head on. Let me get back to sharing the screen here. And okay, so great questions so far. So we'll get right into kind of answering that question a little more. So what moisture content should your wood be, right? And you probably hear all the time in the woodworking magazines, if it's going to be inside, you want it to be 6 to 8% moisture content. Have any of you heard that? Nod your head, shake your head. Never heard that before? 6 to 8. Very good. Well, is that true? One. And two, what does it really mean? Because do you think inside your house in the summertime that the moisture content of wood is going to be 8%? It depends, right? So what does this do for us? Well, 6 to 8 is kind of the average, kind of one of these, lick your thumb and put it in the air. It's kind of an average, right? It's in between where we think wood is going to go between summer and winter. And so if we're in the middle of that difference, we're going to reduce the influence of those changes that happen throughout the year. And that's why we always say 6 to 8. And typically an interior environment that's heated with heating and cooled with air conditioning, it's going to be a pretty close average if we look at the moisture content throughout the year for the average of the United States. Now notice I keep saying the average, because in my opinion, the conditions that you want the final product to be exposed to is what you want for your moisture content of your wood, whether it's in your shop, whether it's in storage, whether it's going somewhere. For the life of the product, it should be based on the area that it's going to. And I'll give you an example. So this is a map of the United States showing the interior moisture content, or I should say the moisture content of interior woodwork inside homes throughout the United States. So if I go up here to annotate, let's see if I can draw some pictures here. If I go up into the DC area here, the interior woodwork in July is going to be pretty close to about 11%, right? Which is kind of on the upper edge of that 8, right? So if I dry my wood to 8, it's going to swell a little bit if it stays long enough at that 11, EMC of 11%. And so that's important to know, right? It's going to change. And if I showed you a map of the wintertime, it would be down around 5 or 6% interior based on someone who has central heating and air. Okay, but what's very important with this map is take a look at the coast of Carolina. If we go down here, what's the moisture content of interior woodwork down here? Is it 11? Is it 10? It's up around 13, right? And then let's say you're a really good woodworker in the DC area and you've got clients out here in Las Vegas. What's the moisture content of interior woodwork in Las Vegas? Youch, right? If I made it in my basement, if I made it in my shop in DC at 11% and I ship it out to Las Vegas, what's going to happen to that wood? It's not going to stay the same dimension, right? It's going to shrink, and it's going to shrink a lot. So knowing where your woodwork is going, if you're selling the material, or just storing it and using it is really important. So if you're going to be along the coasts, you should actually go for the higher edge of that range, right? Go closer to 8%, maybe 9%, depending on the width of the piece. And then as you move out to the dry zones in the United States, you might actually be closer, want to go closer to 6 or even 5%. Now for a commercial operation, this is really hard to do because you have no idea where your wood's going to go. But for a woodworker, you probably have a very good idea where that wood's going to end up. And so knowing this can really help you minimize the problems that you may see, right? So if I was going to sell woodwork to somebody out in Las Vegas, I'd probably run a dehumidifier in my shop, get the wood down to about 6%, make sure it's dry in there as I was working. And then when I finished that project, I'd send it off and leave my shop back to normal ambient conditions. So be aware of that. 6 to 8 is kind of the average between summer and winter, puts us in the average, so reduces swelling and shrinking. But also, we also need to know where it's going to go because that can influence what's going to happen to our wood as well. All right, so here's this wonderful chart. This chart is based on a mathematical model called the Halewood-Arobin model. It basically predicts the moisture content that wood is going to go to based on the temperature and the relative humidity, right? So the temperature on the left side of this is given in Celsius and Fahrenheit. And I always tell folks, when I was in elementary school 1,000 years ago, I was told by the time I graduated high school, we would be on international units. Well, I'm still a Fahrenheit guy, even though most of my scientific literature I have to convert to Celsius. Relative humidity is up here across the top. I kind of shaded it in blue. Now, someone asked, what is relative humidity and how is it different from moisture content? Relative humidity is the amount of moisture in the air relative to the total amount of moisture the air can hold at a given temperature, with 100% being the maximum amount of moisture the air can hold, right? It's going to start to condensate and come out of there at 100%. So you cannot have over 100% relative humidity. It is a relationship between the amount of water in the air and the temperature of the air. And so actually something called psychometrics, you can actually change, there's a relationship there between temperature and relative humidity. You can actually use temperature to change relative humidity. So that's beyond what we want to talk about tonight. What we want to talk about tonight is the amount of moisture in the air expressed as relative humidity and the temperature of the air are the only two things I need to know to predict what the moisture content of wood will be, right? And so if I can measure those things, I can look at this chart and it'll tell me what we call the equilibrium moisture content would be. Now, the careful thing you need to think about with this chart is this assumes that the wood stays at these conditions long enough to get there. So it doesn't usually tell you what the wood actually will be, but where it's headed. So let's do an example. And I sent this out to you, so you should have this with you if you want to draw on it. If I'm in my office and it's 70 degrees, I wish it was, it's actually colder, but if it was 70 degrees Fahrenheit in here right now, and the relative humidity was 50%, I could scroll across, let's see if I can draw on here, I could scroll across here, right? And I could come down here and get to this number 9.2 rather. There's a decimal in there, it's a little hard to see. So the EMC in my office at these conditions, if it would stay there long enough, would be 9.2%. Okay, and I can look that up then for any of the conditions that are on this chart. It's a really handy chart to have. Okay, let's do another example here. Let me go back to screen share. I wanted to get rid of my annotations there, not jump out of it. Here we go. Let's do another example. Well, before we get there, let me talk about measuring relative humidity. So there's several ways to measure relative humidity. They're all called hygrometers. One is the old dry bulb, wet bulb. You have a thermometer that just measures the air temperature. You have a thermometer that has a wet wick on it. The difference between these two, you can look up on a chart and it'll tell you what the relative humidity is. You can just buy a device that has a hygroscopic material. Usually it's pure cellulose. They put a current through there, through a resistor that's taped onto the material, and it'll measure the temperature and relative humidity for you. If you're diagnosing a problem with moisture in your shop or at your client's house, one of these hobo sensors, it's a data logger, you leave it there, and it'll record the temperature and relative humidity over time for you. These are all handy hygrometers. You can get a hygrometer on Amazon. You can buy them from a place called Omega. You can just search online and find them. The only thing is, the more money you pay, the more accurate the relative humidity portion of that sensor will be. Okay, so let's do some examples. Last Tuesday, when I thought I was going to give this presentation, I looked at the weather channel, right? The weather channel said outside it was 47 degrees Fahrenheit. Here's 47 degrees, and it was 54 degrees outside. So if I had 47 degrees Fahrenheit and 54% relative humidity, which is measure the amount of moisture in the air, what would my EMC be for exterior woodwork? Well, let's take a look. 47 is not on this chart, gosh darn it, but 50 is awfully close for our work, right? I'm a government employee, this is government work, right? So 50 will work. And then 54%, well, that's close enough. 54% relative humidity, 55, that's close enough. I go down, I go across. Woodwork, if it stayed at those conditions, would be about 10.3 over time. And you'll notice that if you've ever air dried material, had a tree cut and stacked that wood and air dried it, it's usually somewhere a little bit higher than that, somewhere between 11 and 12%. And that's why the humidity is high enough outside in Virginia that we rarely get low enough to get down to 6 to 8% where we want to be. Okay, let's do another example. Last Tuesday, I was dreaming of Salt Lake City, Utah, and so I looked up the conditions there. It was 67 degrees Fahrenheit, nice and balmy out there, with a 41% relative humidity. Ooh, it's humid out there. So 41, and if we look at our chart, so 70 is pretty close to 67, and 40 is close enough to 41. the woodwork, exterior woodwork or wood I had drying outside in Salt Lake City could actually be air dried down to 7.7 if those conditions remained long enough. Okay. Just as an example of how different the East and the West can be, one winter I was out in Denver, Colorado at a door plant, and they had the windows and the doors at the plant open, and the relative humidity outside was 20% relative humidity. So you can guess by looking at this chart, if we went over to just look at estimate what that would have been, here's 20% relative humidity, right? And it certainly wasn't over 100 degrees Fahrenheit. So that tells you that wood was pretty dry out at that door plant, right? It was less than 5% with 20% relative humidity. Now, you may think, he's a wood scientist. He's got this chart memorized. That is absolutely not correct. There's no way I'm going to memorize this chart. All you need to do as a woodworker is to memorize probably these first two numbers right here, 30 and 6 and 50 and 9, right? 30% relative humidity in the normal temperature range is going to be about a 6% moisture content. 50% relative humidity in the normal temperature range is going to be about 9. And so if you know, hey, less than 30% relative humidity, it's going to be kind of dry. My wood's going to be shrinking. And if it's 50% and going higher, and my wood's going to start swelling, I might want to, take some measurements. So if you can just remember those four numbers rather, it'll really help you out. And that's when you know you're headed towards a potential problem. Okay, with that, I'm going to stop the share and I'm going to see if there's any questions about temperature, relative humidity, moisture content. Would you be able to share this PowerPoint via email or Dropbox? Yes, I can do that.
Brian, now you said those are the only things you need to know, but if I've got a very dense wood, it seems like my percentage is going to be different than if I have a light wood. It also seems to me that a very dense wood might be capable of taking less generally. Does that balance out?
That's a great question. I would say typically you can ignore that. Okay, that gets a little dangerous because you guys work with some pretty funky woods, but typically you can ignore that. The Halewood Aroban model is actually based on Sitka spruce only, but it applies to North American hardwoods so closely, the difference would be probably less than 1% for the majority of species. Now, if you get into unique tropical hardwoods and extremely dense woods, foreign woods, yes, it will be more off, and you're exactly right. The denser it would be, the more off it will be, the lower the actual moisture content will be. But that model will work pretty much for probably 80 to 90% of the woods that you work with here in the United States. The other thing that can throw that off is a tropical hardwood with tremendous extractive content. So if it's really dark and has a lot of chemicals in it, it's going to be lower as well. It's a great question. Does wood finish? We're going to talk about wood finish at the very end. So I'll get to that one at the very end. It's a good question. Anything else? Yes, young lady's raising her hand. Karen.
Hi there. I'm sorry if you've already answered this. Our power went out, so I couldn't join in until about 10 after. I didn't have any internet. But with that moisture content in this area, if the wood is stored in like a temperature-controlled environment, how long would it take to drop it 1% or 2%, rather than going from green wood to 8%?
A long time.
Okay.
Okay, so then we get into wood drying, right? And so you could actually take green wood, and stack it in your home or in your wood shop, and it will eventually get to the moisture content in that table. So if you measure the relative humidity and the temperature, and notice I use the word eventually. So it could take a year. It could take 6 months. It depends on what the initial moisture content of the wood is and the conditions that you're putting it in, and do you have air movement in there. And so my safe answer is if you leave it there long enough, it will eventually get there, yes. If you want to accelerate that process, you could put a dehumidifier in there or turn the heat up. But then you're starting to get into the drying process. So yes, you could actually bring it into your shop, leave it there long enough, and it will eventually get to the conditions that you want it to be.
How long does it take just to drop it like 1%? Is that is that just a relative?
The problem
Thing as well.
the problem gets into what we talked about earlier in regards to gradient. So you can get the outside of that piece there pretty quickly, but can you get it uniform through the cross section? In other words, the center of that piece is going to take a long time to get there. The surface of that piece is going to get there very quickly. Within a day, with the first 30 seconds of an inch of wood, we'll get there probably within a day or two. But all the way to the center of a 2-inch thick piece, it could take months, especially if the temperature is low. Yeah, so that's why I'm going to be safe and say it depends, right? Then we get into drying, which is a whole unique thing. Yeah, good question though. Yes, Fred.
Fred, so if I listen to your examples you've given, it sounds like most of us should have a dehumidifier in our shop.
You could. So you can play with this chart two ways. You can put a dehumidifier in there, or you could use heat. The problem with using heat is it gets too warm in there, right? So a general rule of thumb is to keep wood at about 6 to 8% moisture content. You want to go about 10 degrees above the morning low. I think it's 10 degrees. Let me look that one up and get back to you about somewhere I've got that. I should have it memorized. I think it's 10 degrees above the morning low or 20 degrees. I'll have to look that up, but that'll give you an EMC. And of course, the morning low is right around 6 o'clock in the morning. And so it means it changes based on the time of the year. So in the winter, that would be really cold, and in the summer, that would be really hot. So dehumidifier is going to help you out better. I think the most important thing is actually for you to measure what the relative humidity is in your shop before you do anything. Find out what it is and see how it changes between the time of the year to see what you need to do. You may not need to do anything, but you may need to do something. And the most important thing is to measure and to use that chart to see where your wood is going to go and what's going to happen to it between the seasons. That's the most important thing. Great questions. All right, let me jump back into, all right, so now we're going to talk about the orthotropic nature of wood. So now we're getting into what's called planes of reference. Okay, so when you saw lumber out of a log, say using a portable sawmill or any sawmill, you're going to get what's called plane sawn wood the majority of the time. And that's the boards over here on the top of that piece that are on the left. And how do I determine if they're plane sawn? Well, these little circles in the log are called annual growth rings. You may remember as a child counting the growth rings on a tree to get the age of the tree. That's basically 1 year's annual growth. Some species, it's really easy to see that, if you remember our wood ID class. In some species, it's really hard to see, but you can generally see these in a piece of wood. Whoops, and I went backwards there. And you can see in this is a cross section. Look at the end of a board. This would be a plane sawn board, and you can see those growth rings are through the width of the piece, nicely arranged through the width of the piece. That's a nice piece of plane sawn wood, okay? Quarter sawn, a lot of woodworkers like to use quarter sawn, and we'll talk about why in a few minutes here, but quarter sawn would come out of this piece of the log right here, and you'll note those growth rings are actually about perpendicular to the width of the board. That's pretty interesting. But notice as you move from one edge of that board across to the center, that they begin to curve more. Why is that? Well, if you look at the growth rings in the log, as you get from the outside of the log to the pith, those little circles get smaller. Those growth rings get smaller. Now, this is important. We're going to come talk about this as we move forward. But generally speaking, quarter sawn, these growth rings are not, a perfect quarter sawn piece is a 90-degree angle of the growth ring to the width of the surface, right? We can argue where it turns into rift versus quarter when the angle gets a little steeper, but that's something you can argue with beer and lots of time. But basically, the more up and down that is to the width of the piece, the more quarter sawn it is. Okay, so we've got plane sawn, quarter sawn, and I can tell the difference by looking at the end grain and looking at the growth, how the growth rings are presented in that end grain. Now, before we move on, you'll notice though, in this plane sawn piece, look at this edge. Wow, that's different. That's actually got the growth rings looking like this piece of quarter sawn. And in the quarter sawn, if you look at the edge actually looks like the width of this piece, like the plane sawn. That's why we need to talk about planes of reference. We need to define what these are, because wood is an orthotropic material. And what does that mean? It has different mechanical and material properties in each of the different dimensions. It's one of the fun things about wood, right? So let's talk about where this word tangential comes from. If you can think back all the way back to high school geometry, if you drew a circle and you drew a line perpendicular to the center of that circle, we would call that a tangent, right? So if you notice, when we saw those boards out of a log, the width of those boards is pretty much tangent to the center of that circle. That's why we call that plane of reference, the width. The plane of reference is called the tangential plane of reference. And one of the things you'll notice in this drawing is my nice, beautiful drawing I gave you in the beginning. Notice the uniformity of the growth ring between the top of that piece and the bottom of that piece. Notice how beautiful that is? That means that the top of that piece and the bottom of that piece are both tangential planes of reference, right? That came from a really, really big tree, right? What we saw today, the average sawmill, the average hardwood sawmill in the United States, their average log diameter is 12 inches on the small end. That's pretty small, right? So you're looking at a log like this where the growth rings are pretty curved. And so when you produce that plane sawn piece, notice the curvature of the growth ring in those pieces, especially as I move closer to the center. It's not as pretty as this nice drawing I did for you. And we're going to talk about what that does in a few minutes. But it's important to notice the curvature of those growth rings in those plane sawn pieces. And I'm talking about in relation to the width of the board. So here's a pretty plane sawn piece of oak. You can see the growth rings is not as pretty as in the picture. You can see how they're represented in here. You can see the average growth rings. Here's 1, 2, 3, 4, 5, 6, 7 years of growth presented in this piece. Pretty typical piece of wood. Quarter sawn is the width of a quarter sawn piece we call the radial plane of reference. Well, if you think about a circle, draw a line from the center of that circle out, we call that a radius, right? So if we saw a board where the width of that board comes pretty much from the center of the tree, note those growth rings, right? This is basically pretty close to a radius. So we will call that plane of reference the radial, okay? And to get pure quarter sawn pieces, well, I'll say pure and a small log, you'd only get 4 pieces, right? It would look like a cross and you'd get 4 pieces out of there. Another thing about radial is you'll see these little lines here. We call these wood rays. They move water in this direction. And when you cut quarter sawn material, you split those and it actually gives you nice looking figure, right? Here's a piece of quarter sawn southern pine. You can see I actually dented it in a hardness test. This is a piece of flooring. You can see how those growth rings are pretty much perpendicular as you move across that piece. But notice out here where the sapwood is, that's where the bark was, how purely perpendicular they are. And then as you move towards the pith, they begin to curve, right? It's still a quarter sawn piece, but we're starting to see a little bit of change. We'll talk about what that's going to mean in a minute here. Okay, so the orthotropic nature, right? We know tangential and radial at this point. In a plane sawn piece, the width of the board is going to be the tangential plane of reference. In a quarter sawn piece, the width of the board is going to be the radial plane of reference. So what is the thickness in a plane sawn board? Any guesses? That's going to be the radial plane of reference. What is the thickness in a quarter sawn piece? That is going to be a tangential plane of reference. So here's a little rule of thumb about shrinkage and swelling of wood. Wood shrinks twice as much tangentially as it does radially. Now that's another rule of thumb, right? You get into some foreign species, a lot of extractive content. It's not exactly true, but for most North American species, it's a pretty true rule of thumb, about twice as much. So the width of a plane sawn board, because it's tangential, is going to shrink twice, percent-wise, it's going to shrink twice as much as the thickness. Okay? A quarter sawn board is going to shrink in thickness, percentage-wise, twice as much as it does in width. Okay? So that makes quarter sawn boards in width very dimensionally stable compared to a plane sawn board. The other thing I need to mention at this point is the length of wood, right? In length, the length of wood, wood shrinks negligibly in length. It's about 0.1%, 0.1%. Okay. I've got a question from somebody's got their hand raised. You want to go ahead and ask your question? I can't see your name. We'll come back to it. Okay, so right here, this is typically what you're going to see. More of the plain sawn wood that you're going to pick up is probably going to be closer to this piece here. Maybe not as drastic. Let's hope not quite as drastic as this. But this would be cut out of a small diameter log. You can see the pith, which is the center of the tree, is going to be down here. The bark is going to be up here. Now tell me, the width of this board, is it plain sawn or is it quarter sawn? Well, it's a plain sawn board. I told you that. Is it going to be more tangential on the top or more quarter sawn? That's kind of hard to tell. So since you can't really talk to me, I'll tell you. The top of this board has more plain sawn plane of reference, or excuse me, tangential plane of reference than does the bottom. You can see it right here. Let me annotate this a little bit. This area right here is pretty pure plain sawn, or I mean tangential. This area right here is about the only pure tangential. As you move out into this region, it's somewhere in between, right? In this region, somewhere in between. But when you get down here, it's really close, but it's not exactly radial. So looking at this piece in general, the top portion has more tangential plane of reference than the bottom portion. So we know that the top portion, as it dries, is going to shrink more than the bottom portion. Why? Because there's more tangential plane of reference on the top than there is on the bottom. And what does that do? Well, that leaves us with a piece of wood that looks like this. And I apologize for the blurriness. I couldn't find my original picture with it that was as sharp. But you can see this is a stack of lumber that's drying it from a dry kiln. This is a piece of yellow poplar. You can tell that this is the heartwood. So you can tell the pith was down here. You can see the growth rings right here. And so you can see from this piece that there's more tangential plane of reference on the top than there is on the bottom, kind of like my diagram. Not quite as drastic as my diagram. And so as the wood dried, it was able to shrink more on the top, and so you end up with cup. All right, now you might say, Dr. Bond, look at the piece next to it, it's the other way, so what you're saying can't be true. Well, that's a sneaky one because they just flipped this board over. See, here's the heartwood. This is the sapwood. You can actually see some bark here. So the bark was out here, the center of the tree was here. You can see the curvature of the growth rings. So it did exactly the same thing, right? Yeah, the more tangential plane of reference shrank more than the bottom, and so it cupped. But then you'll say, Dr. Bond, something doesn't make sense. These other boards look really flat. Well, you'll notice in the stacking here that there's no pressure holding these boards together as the wood is dry. Whereas here, you've got weight distribution through the entire pile holding those boards flat. And these boards are a little bit more quarter sawn, which is why they're more flat. And I apologize, you can't really see the grain there. This is a classic example of why wood cups. Wood naturally cups when you have a plain sawn board, especially when the curvature of the growth rings is extreme across the width of the piece. Okay? If you're able to cut a redwood tree down and get something like this, it would not cup. If the top and the bottom have the same pattern of growth rings, it's the same plane of reference. If the plane of reference is equal, it will not cup. This is one of the reasons why quarter sawn wood is so desirable, is because you're pretty much going to have, if you have a true quarter sawn piece, you're going to have the top and bottom surfaces in width are going to look very much the same and have the same plane of reference. And so they cannot cup. It will not cup unless you see a great difference in the angle of the growth rings between the top and the bottom. That's a lot to take in, right? But just the sheer fact that a piece of wood can have different amounts of the plane of reference in top and bottom can cause wood to warp if the moisture content changes. That's normal wood. Let's talk a little bit about abnormal wood. There are two kinds of abnormal wood. One is called reaction wood because it's a reaction to how the tree grows. Typically, this is found in a leaning tree. Okay? The second is juvenile wood. All you really need to know is for both of these, they shrink in length a whopping 1%. That's right, you heard me, 1%. But remember, what does normal wood shrink in length? Anybody remember? It's about 0.1. So that tells me that abnormal wood shrinks how much more? 10 times more in length. than normal wood. That's where the problem comes up. So reaction wood is tension wood and hardwoods, compression wood and softwoods. It's an abnormal wood. It has different chemical composition, different microfibril angles. You can see it sometimes. So this tree was leaning. It's a hardwood tree. It was leaning, and the tension side tried to pull the tree back up straight. So it put abnormal wood fiber on the leaning part of the tree, the tension side, and it tried to pull the tree back up straight. And so that wood is going to cause problems for you. Juvenile wood is around the pith. It's around the center of the tree. Juvenile wood is put down as the tree begins to grow. Its goal is to grow as high and fast as it can. And so that juvenile wood also has different chemical composition, and it's also going to shrink more in length than what we call mature wood. And most hardwoods, juvenile wood is somewhere between 5 and 8 years of growth. In pine trees, it could be as much as 20 years of growth in, say, a plantation pine. So here's another example between really old growth wood versus new. You're probably going to see very small juvenile wood zones in old growth material versus plantation pine. So literally, some of the pine trees we harvest today with a 30-year rotation, over 50% of that wood is juvenile. Kind of interesting. So what does that mean to us? Well, here we go. So this is what we call bow. And this particular species is called Ailanthus altissima. It's tree of heaven. It's a weed species in the state of Virginia. It's invasive. The state of forestry, Department of Forestry cut some up for us, and we dried it for them. It has a lot of tension wood in it, okay? So the top surface of these boards, this top part, shrank up to 10 times more than the bottom, which was mature wood, and it causes it to pull up like that. Now, when I say shrink, I mean shrink in length. What causes bow to occur? One surface shrinks more in length than the other. It has to. What else could possibly cause that except holding it in that position while you were drying it, okay? So bow has to be caused by either reaction wood or juvenile wood. Crook, you can see this wonderful pine here, or this might be some of that ailanthus. This is called crook, where it bends to one edge. Crook is caused by the same thing. It's either juvenile wood or tension wood. This edge contains the juvenile wood or tension wood and shrinks up to 10 times more than the opposite edge. And you may say, well, how is that possible to get juvenile wood only on one edge? If we look at this tree, you know, I just mentioned that quarter sawn is some of the most stable wood, but this particular piece of quarter sawn labeled A would potentially have juvenile wood on this left edge. So this left edge may shrink up to 10 times more than the right edge and cause that beautiful quarter sawn wood to crook, right? Samples B and C are going to be fine on these outer edges, but this top right corner in B and the top left corner in C probably contain juvenile wood, definitely do if this is a piece of pine, because it's well within the first 8 years of growth. So you're going to end up having more length shrinkage here on this edge than this edge, causing it to crook, right? And so looking at how your wood is sawn by looking at the end grain can really help you predict what wood is going to do. Or if you're the sawyer, sawing a pallet cant or a big square out of the center and getting your grade boards elsewhere is going to help you get straighter lumber. Twist. Now, twist is caused by several things, but one of the main reasons of twist is angled orientation of the wood cells. So if you think about a normal tree, we'll say normal, most trees, the growth rings, the cells are oriented from the roots to the leaves in a straight line. So if you've ever split firewood, split some oak, you know that you hit that wedge and it goes straight through. Beautiful straight grain. Straight grain is going to produce flat wood. If you look at this wonderful white bark pine that's been dropped on the ground here in this bottom picture, notice the spiral. So the wood cells are actually oriented almost perpendicular to the growth axis of that tree. That's a pretty good angle, right? So imagine water trying to get from the roots to the leaves. It's going to have to spiral all around that to get to the top. So if you saw a board out of that piece and you dry it, what do you think that board's going to do? It's going to try to go back to, right, gain some, it's going to twist as it dries to kind of go back, affected by the orientation of the wood cells as it was in the tree. And that's why you see on the joiner here, the twist in this board, there's some angled grain in there. So Species that are famous for angled grain would be things like sweet gum, black gum, any species that has tension wood in it. And another interesting one is hickory. Hickory will have grain going in an angle this direction in one year, and then the next year it will go in the opposite direction. We call that cross grain, and that's one of the reasons why hickory is so hard to split, is because of that cross grain. Okay, so if we could only predict what wood is going to do when moisture changes, it would be like having Zoltar give us the secret. We could prevent bad things from happening, but guess what? We can do that, right? We can do that knowing just a few things that we've learned tonight. For normal wood, it's not too hard to predict these things if we have a uniform plane of reference. So let me give a classic example of seeing some of this. A beadboard tabletop is a classic example of seeing moisture changes in a piece of woodwork, right? We know that typically in the wintertime, we'll see the width of the table shrink. And why is that? Well, we know now that the tangential plane of reference shrinks twice as much as radial, but also that wood only shrinks about 1% in length, right? From green to dry. So the length of this piece is hardly moving at all, but in the wintertime, the width of this table is moving significantly. But notice also, it's shrinking a little bit in thickness, and you can see that in the bead, right? So it's shrinking in width and thickness. And then of course in the summertime, depending on when this piece was made and cut, it could actually stick out the opposite way, right? So it's a classic example of visualizing and seeing wood shrinkage and swelling happening. So let's do some math to see if we can actually predict what wood is going to do. So there's a calculation for everything if you're an academic. So here we go. This is straight out of the wood handbook. If I want to know how much my tabletop is going to move, that's delta D. That's how much movement I'm going to have, right? D1 is my original dimension. SO is something we call the shrinkage value. The shrinkage value I pull out of the wood handbook. You can look it up online. It is basically the amount of shrinkage that wood is going to do from a green state to oven dry. Well, we're not going to oven dry it, right? We're going to dry it to 6 to 8% moisture content. We're going to be using some range. So that's why you see the moisture content in here. You take your initial number, you subtract it from your final moisture content, and you divide that by 30. You might say, well, why 30? That seems like an odd number. 30 is the fiber saturation point for most North American hardwoods, somewhere between 28 and 30. A wood cell, notice I said a wood cell does not shrink until it drops below 30% moisture content. That is not a block of wood. That is not an average moisture content. That is the moisture content of an individual wood cell. We call that the fiber saturation point on the oven dry basis. So that's why we have this little moisture content portion of the calculation. So let's use it. There's no better way to understand a calculation than to use it. Before we do that, I'll just say this is table 3.5 from the wood handbook. It lists domestic species, foreign species, hardwoods, softwoods. You can find most tangential and radial shrinkage values for most domestic and foreign species in the wood handbook. I've given you this particular one. It lists some very common species. We'll use it for our examples tonight. One thing I'd like to point out right now is, we say when we buy oak and we buy red oak, we typically say, hey, I've got a piece of red oak. But notice in red oak, there's actually 12 species called red oak. And the lumber is typically sold as red oak. Notice the tangential shrinkage value between northern and southern red oak. It's pretty significant. And we'll see what that could potentially mean to us. But sometimes knowing what the exact species you're using can be very helpful, because southern red oak is less dimensionally stable than northern red oak, but when we buy boards, it's just called red oak. Okay, let's do an example. So I made a tabletop that was 3 feet in length, or I should say width. The width of the wood was 36 inches. It was red oak, it was southern red oak. I made it at 8% moisture content, and I know that burning wood in my house is gonna cause that wood to absolutely reach 6%, if not lower, in the wintertime. How much is that tabletop gonna shrink? Well, that's a good question. I don't want it to end up with this crack in there. I definitely want that table to be able to float, but just how much do I have to worry about? So delta 1 is my initial dimension, which is 36 inches. S sub O is my shrinkage coefficient. Well, if I go back to my diagram here, Southern red oak could be 4.7% or 11.3, but I know that my tabletop is plane sawn, so I'm going to use the tangential plane of reference, right? Most plane sawn wood, the majority of that width of the surface is tangential, so I will use a shrinkage value of 11.3. Be careful because that's 11.3%. We're going to have to change that into a decimal. And I made it at 8, so that's my initial moisture content, and my final moisture content is 6. So how much is it going to shrink? Well, let's plug in the numbers. So I convert my 11.3 into a decimal, so it's 0.113. I take 8 minus 6 is 2. 2 divided by 30, 36 inches. That tabletop is going to shrink about 0.27 inches. That's about a quarter of an inch. Does that seem like a lot? Let's put this in perspective. How much moisture content did we lose just to get a quarter of an inch change? We only lost 2%. What if I shipped this table from DC out to Las Vegas and I went from, say, 12 to 4%? How much is that table going to move? We're getting up there, right? Almost a little over 3/4 of an inch just with that change. That's a lot of movement. I'm going to have other problems as well, but I better made that tabletop able to move on there or I'm going to split it, right? So there's an example of how we calculate. Let's do another example. So how much dimensional change would I expect in a 10-inch wide hard maple panel if it goes from 6 to 12% moisture content? Well, what would a hard maple panel be? That could be a panel in a cabinet, a floating panel in a cabinet. That could be something I made for drawers. But a 10-inch wide hard maple panel goes from 6 to 12%. What does that mean? I made it in my shop at the right moisture content. My client lives on the coast. They leave their windows open all the time. It's going to move. How much is it going to move? So my delta is my 10 inches, or excuse me, my D1 is 10 inches. My shrinkage coefficient, I can look that up on the table there, is 9.9 because this is also going to be a plane sawn piece of wood. My first moisture content 6, my second moisture content is 12, and I'm going to end up with just over 3/16 of an inch change going from 6 to 12% for that 10-inch wide piece. Not terrible, but if I pin that panel in a floating and not made it floating, it's going to cause problems for me. So you can see if I can use the chart with temperature and relative humidity to figure out what my moisture content will be, and I know what my moisture content is using a moisture meter, I can predict very accurately what my wood is going to do, right? With pretty good precision. And so I can design in how much movement I'm going to allow for that piece of wood when I'm making that piece or designing that piece. Or I can see what's going to happen if my client lives in conditions that are drastically different from what I have. So we can use those calculations to do that. So this is all too much. I don't want to do it. Can I just avoid all this stuff? If you can keep the temperature and relative humidity constant from when you begin to process that wood through its manufacture, through storage, and in the client's home through its service life, you shouldn't have any problems with wood movement. The problem is that it's very difficult to do. We know that relative humidities and temperatures change in a home environment between summer and winter. It happens all the time, right? So what can we do? Well, one of the things you want to do in this diagram at the top is when you make wide pieces, wide planks, glued together planks, you want to make sure that the orientation of the planes of reference, or I'll say the orientation of the growth rings and the end grain, are the same for those pieces. Okay, the more radically different they are, the more you're going to see those pieces move differently, even if they're glued together. Okay, so the example here is you get a plane sawn piece and two, I'll call them rift sawn or quarter sawn pieces. If the moisture content drops 2%, you end up getting some differences in the thickness of that table. And you can notice this if you go to a lot of restaurants. Don't necessarily have the highest quality solid wood materials. If you look at the light shining on the tables at most restaurants, you can see this these changes occur in the piece of wood. It's kind of interesting. You can see the the shadow effect with the light on there. Another thing you have to avoid in really wide tabletops is using the same plane of reference, the same direction throughout the width of the piece. So if you orient the grain the same way, you can end up with a situation like this where the whole thing cups because every single piece has the greatest tangential plane of reference on the bottom and the lowest on the top, and so it's gonna cup just like it would normal wood, right? However, if you flip it every other one, you can sometimes get this washboard effect if you get great moisture content changes once it's made. So the rule of thumb is make sure your wood is dry to the right moisture content to begin with. Make sure it's uniform in thickness. You don't have a gradient in that piece when you start, and try to maintain your moisture content through the manufacturing process. If you have to do really wide tabletops, what's the most dimensionally stable wood to use? Well, it doesn't matter what species, it's the quarter sawn boards that are going to be the most dimensionally stable, right? Generally speaking, and you won't like this, but generally speaking, really wide planks are going to move more than a bunch of narrow planks glued together. Why is that? Because you're typically going to have more curvature, more difference in the growth rings, looking at it from the end in a wide piece than you are shorter pieces all glued together, right? And so that's something to be aware of and wary of as you move through. Now, someone asked about finishes. Of course, finishes are great. Now, this is a page out of the wood handbook. I don't expect you to read it all, but I'm going to pull polyurethane because it's a common, most beginner woodworkers use polyurethane. Polyurethane just happens to be a very good finish for reducing moisture uptake. Now, no finish out there is 100%, with the exception of paraffin wax. Well, even paraffin wax isn't 100%. No finish out there is 100% given long enough. Moisture will pass through polyurethane. Okay, just an example here. This is the number of coats. This is the effectiveness over 1 day, over 7 days, and over 14 days. And you can see the more coats you apply, the more effective the finish is at reducing moisture uptake over time. Yes, eventually it will get there. But the goal of the finish in regards to moisture is to reduce that enough that conditions will probably change anyway, right? They'll probably close those windows. The heat will come up. The relative humidity will change within 2 weeks' time. So it'll never reach potentially the worst conditions possible. In other words, you're slowing down the effects and reducing moisture uptake and loss, therefore reducing moisture movement. Now, not many people like 6 coats of polyurethane on their furniture, but it's significantly more effective than 1, right? The more coats you add, the more effective it is. And that's pretty true with all finishes. Now you can go through and see, let me back up here. You can see, a lot of people like linseed. You can see how ineffective linseed oil is and tung oil is relative to something like polyurethane on this graph. Several coats of linseed oil within 7 days, it's only about 2% effective. Paraffin wax, which no one wants to use, is very effective, right? But it's still going to allow some moisture to pass through. It's not a perfect coating. And you can look at this table in the wood handbook and compare your finishes. But basically, the more coats you have, the better off you're going to be in regards to moisture protection. That's what we're talking about, okay? All right, so I've covered a lot of material. I've thrown it at you. I think we've covered, the basics pretty well. We're all smiling at this point, I hope. Some of you look like you're pulling your hair out, but I'm going to open it up for questions and we'll see what happens from there. So what about a wide plank cutting into thinner planks? Well, it depends. That's the first question I'll answer since it's up here. Wide plank is what you want because it's a beautiful piece of wood. The more curvature, the more difference you have between the top of that plank and the bottom of that plank in regards to the orientation of the growth rings, the less stable it's going to be with moisture changes. So if you've got a wide quarter sawn plank, I'm fine with it. If you've got wide planks cut out of a small diameter tree, I'd cut it up. I'd cut it up and try to vary the pieces from different locations in the tree to try to make it more stable. It's a good question. Does wood finish mitigate the effects of moisture on wood? I think we just We just talked about that. It's not that the equations are changed. It's just it changes the amount of time it takes to have moisture uptake. It reduces, it lengthens the time you have before those changes occur. So hopefully the relative humidity will change in those conditions before you actually reach that EMC. It's a good question. Anyone else?
Brian, could you talk about the tangential radial shrinkage and incompatibility of woods with large difference in ratios?
Okay, so you sent that question to me and I was a little perplexed. So are you talking about gluing them up in panels?
Yeah, it could be gluing up in panels, or we have face-to-face grain glued together.
Okay. Sure, let's see what else we have here. All right, yeah, here we go. So this is Fred's question. He asked it to me a couple days or about a week ago, so I threw it on here. Generally speaking, if I'm going to glue planks together, I don't care. Generally speaking, if I'm gluing planks together, I don't care. And why do I say that? Think about plywood. Think about plywood as a piece of plywood. If I'm edge gluing pieces together to make panels, I'm never going to have the stresses in those panels, regardless between radial and tangential, that I would have in a piece of plywood. So if you think about plywood, the one layer, the wood is oriented this way, and the next layer it's oriented this way. So you've actually got tangential plane of reference restrained by longitudinal. That's a huge difference. So from a structural point of view, I'll make that quantification. From a structural point of view for the glue joint, I don't actually care. The glue joint, I don't believe is going to fail if it's a proper glue joint. I'm going to be more worried about density differences because really highly dense woods are harder to glue. I'm going to worry more about extractive content because woods with high extractive content are going to be harder to glue. However, I will agree with you in regards to what can happen in regards to the visual characterization. So yes, you can have pieces that will look funny because one will shrink and swell more than the other, which is probably why he uses that. I also worry in this particular example, this is engineered wood flooring where you have plywood and you have a face veneer on top of that, which would be gluing veneer. You have to be very careful in these situations because the glue, if the glue bond is good, it won't fail. I still stick with I don't worry about the structural integrity of the glue bond. But this thin wear layer can actually have enough power as it shrinks, enough influence that it can actually override the plywood underneath and cause that piece to cup. So having large differences in face gluing like this, yes, makes a big difference. And I would agree with minimizing those differences as much as possible. But I think from a glue joint structural integrity point of view, it doesn't matter. Does that make sense? So I would agree keeping them as close together as possible makes complete sense in regards to visual appearance. But I think from a structural point of view, I have other concerns. Good question. Does the thickness of a board change how it will warp in its plane? That's a really good question. And the answer is yes, because you can have some drastic differences in a really thick board that you may not have in a thinner board. And typically, in general, with the exception of cup, thicker boards tend to warp less, which is interesting. I would hope you aren't gluing quarter to, yeah, me too. But, people do strange things. Matter of fact, I've seen just about everything. So I have seen plain sawn and quarter sawn glued together. And yes, it did not look well after there was a moisture content change. Why does plywood warp so much? Well, theoretically, plywood should not warp so much. One of the problems with plywood is in the manufacture. If they don't get the moisture content correct, it creates warp in the manufacturing process, actually. And they dry those veneers so fast. I mean, they dry those veneers in a matter of minutes using very high temperatures. And sometimes, particularly in pine plywood, structural plywood, They create warp by having incorrect moisture contents when they glue up those panels. And so that's one of the reasons poorly manufactured plywood does warp. Well-made and manufactured plywood should not warp and should actually be more dimensionally stable than solid wood. It's a good question. The layers in the crap from Home Depot and Lowe's isn't the same. No, it's not actually. So you say the crap. Let's quantify the crap. So when you buy pine from Home Depot and you buy 2x material, that material is actually dried to a higher moisture content. It's usually dried to 19% moisture content or 15%. And so it is actually at a higher moisture content to begin with. If you're talking about the hardwoods that they sell, it should be. It depends probably how long it's been in the store. Their suppliers are actually pretty good at drying. It could be how that material was stored and handled. But usually the hardwoods they sell in pretty small quantities, is actually manufactured by some good manufacturers. It may just not be handled well. It isn't that, and so I would always check wood, whether I get it from Lowe's, Home Depot, or anywhere. If I'm bringing it in the wood shop, I'm gonna have a moisture meter of some kind to check the wood all the time. I'm always gonna do that, and I'm always gonna look for a gradient, because most of the wood, when I was in college, I used to buy wood from a local guy that had a dry kiln, and it was always wet in the center. And here I am studying wood scientist, and I always learn the hard way that I should check the moisture content within the thickness. Are checks caused by moisture issues? Okay, so an actual surface check, in my opinion, is caused in the drying process, and not by moisture content changes. A split can be caused by moisture changes. End splits can be caused by moisture changes, but typically a surface check is caused in the drying process. They are often closed at the end of the drying process, so you can't see them, and then they reopen as the surface dries out. How can you prevent boards from checking? Maintain that moisture content all the time. I would worry more about end splits. The ends of wood absorb and desorb moisture 10 to 15 times faster than the transverse surfaces. So watch the end grain if your environment in your shop is going to change drastically while those pieces are in there. Oh yeah, pressure treated wood is wet. It is actually saturated when you buy it, because most pressure treated lumber is treated with chemicals that are waterborne. They put the chemicals in water, and they actually impregnate the wood with water. So they actually put water into the wood using pressure. And so they don't dry it when it comes out, because we're silly enough to buy wood that's dead green. You can, if you're a contractor, buy kiln dried pressure treated wood so that it doesn't warp. But most of us buy it from Home Depot and Lowe's. It's dead green and it's going to dry. So it depends on whether you're leaving it outside or not, and what you're going to do with it. It takes a long time to actually dry, and it usually warps if it's not installed right away. How long can it be finished? Usually a couple of weeks, because the surface will dry before the piece does. But you don't want to go too many months, because you'll get what's called surface inactivation. In other words, the sun will begin to bleach that surface, and then the finish may not stick as well. So give it a couple of weeks, maybe 2 to 3 weeks before you do that. If a check is from the drying process, is that just a weird board or dry? No. Checking in certain species is very common in the drying process, particularly oaks. Someone said there are plain sawn white oak surface checks really easy. Yes, it does. And part of that is because it takes a long time to get uniform moisture through the thickness of the piece. And so the outside has a lot of stress on it in the drying process. And it also has very wide wood rays, which are a weak spot. Those wide wood rays in white oak cause a lot of problems. The fact that it's dense and has wide wood rays, you have to dry it really slow. So if you dry it really slow, it will not surface check on you. Good question. What else? Is everybody pretty cooked? Very good. So if you have any questions, I'll give you another couple minutes. And otherwise, we're done. So I'm going to go ahead and stop recording.